Welcome back, gentle folks. Today we're going to talk about all about amines. We last introduced the amino group last week on Friday, and we talked about how classify amines as primary, secondary, tertiary, and quaternary based on how many carbons they're attached to. So let's talk about the basic IUPAC scheme. Now, they're going to be very similar to how we did alcohols, except a little different. So, basically for IUPAC scheme, we have an alkyl and use alkane, alkene, alkyne, and we take the E off and change the ending. So in this case, we're going to take the E off, remove the E, and it's going to change to an amine. I know that's a little bit longer, but with it, and the numbers typically before it, like if I had this, I could call this propane 2-all. Now, if I did the same thing with amine, I would have propane 2-amine, propanamine. So the 2 shows the position in the propane group. Now, if there is carbons attached to here, we're going to introduce on a numbering system of N, or we say instead of 1, 2, 3, we're going to have things N substituted. So N shows attachment to the amine as a substituent. So for example, if I go back with I would call that, so that's a 1, 2, 3, 4, 2-butanamine, but I would call that N, N dimethyl butanamine. N dimethyl butanamine, where we're saying the methyls are not attached to the butyl group, but it's attached to the amine. Now, let's note that the nitrogen cannot be chiral. Cannot be chiral. This is due to something called the nitrogen inversion. Essentially, so long as there is a lone pair in there, so long as there is a lone pair in this group, primary, secondary, and tertiary amines cannot be chiral because there is so looking at it from this, there is an inversion that can occur. It's a small energy inversion, but it is an inversion nonetheless. Here, it's a 25 kilojoule barrier with a lone pair to swap from one phase to the other, but it uses the p orbital to get there. So what this means is that this occurs hundreds of times per second at room temperature. And so by itself, this is not necessarily a chiral center. Now, in order to be, we can still have chiral carbons to make a chiral amine. So if you have a chiral carbon, like so, this is like, this is a chiral center right there. So we can still have that being chiral, but the amine itself is not chiral. So you can still have chiral amines, just not necessarily that way. If you have quaternary nitrogen, you can have chiral, as long as all the groups are different, because there's no lone pair in a quaternary amine. You have 4 carbons coming off of there, so you can't see the inversion. And the third way you can get a chiral amine involves a ring system. So, it's when we cannot get sp2 hybridized, so we cannot interconvert. So, like in those, in those situations where typically nitrogen is sp3 hybridized in these amines, but we could temporarily shift into an sp2 hybridized with the lone pair in the p orbital. So essentially, the amine goes from tetrahedral to shifts lone pair, doesn't really matter where, shifts to sp2. sp2 electrons are going to shift down to there. So we get our back to sp3. Now, anytime the nitrogen cannot adopt an sp2, this is that energy barrier. You cannot see an interconversion. So, for example, small rings, like we talked about this one last, aziridine rings. Now, because of the strain on this ring, it cannot switch out of sp3 to go to sp2. So the inversion is particularly slow. So we're not really going to see an inversion in this 3-membered nitrogen amine ring. So there's something to keep in mind when we look at chirality and isomers. Okay. Now the properties of amines. Amines are polar. They will create hydrogen bonds, but they are less polar than hydroxide. So if you compared the boiling point of alcohols to amines, amines are going to be significantly less. So NH2 amines and NH amines. So primary amines and secondary amines are going to be about the same, but they're going to be much, much less than tertiary amines and ethers. Why would they be about the same? Well, no hydrogen bond. So strong hydrogen bond, strong H bond, weaker H bond, and then, of course, in the tertiary amines and ethers, you have no H bond. They can still get dipole-dipole, but there's no intramolecular hydrogen bonding you can see. So now all of these amines, primary, secondary, and tertiary, can all hydrogen bond except in a and a protic solvent. So they're going to be really good for dissolving in anything with any alcohols. And of course, so some of these amines are known for their smells, especially diamines, or smell really bad. I mean, we know 1,4-butadiene is putrescine, and 1,5-pentadiamine is cadaverine. These guys are going to be produced as the body starts to decompose. So these smell of dead flesh are going to be made up of diamines. So if you ever smelled like something crawled into the vents and died, and you like get a whiff of something really awful, that's the diamines being produced. Now, unlike many of the alcohols, these are usually rather basic. So there's a degree of basicity that's not typically seen on some of the OH groups. So amines will act as a Lewis base. So remember, Lewis base doesn't have to just accept a proton, they can also be nucleophiles. So they could be a nucleophile, but they could also be the traditional Bronsted-Lowry base when it comes to protons. So weak aqueous space, in water, they're weak aqueous spaces. So they're not great bases in water, but they are still bases. But typically, they're still a stronger base than standard water. And if you compare the KB, stronger base than water. So anything that's donated in proton will probably go to them first before it goes to water. But OH is still stronger than them. So in terms of basicity, just put OH minus then amine H2. So now primary, secondary, and tertiary amines are moderately strong bases, having a PKB between 3 and 4.5 for most amines. Now, if you get to aromatic nitrogen, they are not very good bases. So aromatic nitrogens, like those they're pretty weak. A PKB between 8.7 and 13. They can accept something, but they really don't want to. And in some of these heterocycles, it all depends on what type of nitrogens we have. Some of these guys will be a little bit more basic than others. Now, so factors that will affect the basicity of these guys. So, factors those, but things like electron donating groups, donation. Donation will make a stronger base. So if we have some alkyl groups, so we're going to have a stronger base. Donation. Alkyl groups. However, solvation is going to be a factor. So steric hindrance will decrease solvation and thus decrease basicity. So that means secondary amines are going to be more basic than primary, but both are more basic than tertiary, because the water has to get in, the solvent has to get in and get by there. It's not going to be able to be a good nucleophile if you can't get to the lone pair. It's not going to make a good Bronson-Lowry base if you can't get to the lone pair. So even though a third group would be donating more density, you can't get to the lone pair, so it weakens that. Let's strengthens. Weakens. Now resonance. If resonance delocalization of the non-bonding electrons will reduce the basicity. Pair weakens. So if the lone pair can be used in other double bonds, it's not going to be as available to act as Lewis base. So like aniline. Aniline, we can donate this lone pair into this ring and thus conjugate it. So now, and so that guy actually has a PKB of 9.4. Now direct resonance into the will lower the basicity even more. So like say pyrrole. So in this case, you don't need that lone pair to make this aromatic. But this guy, you do need this lone pair because the 6 rule, 2, 4, 6. You need that lone pair, so that lone pair is being used. That guy will not want to donate at all. So that guy is 14.3. That is really going to be really hard to pronate that nitrogen. And the last effect, well, I want to say the last effect, but hybridization effects. Orbitals will, with greater S character, will hold the electrons stronger. So that means S character. So if I say SP, that's made of one S and one P. SP2 is made up with S character, percent S. SP2 has one S and two P. And SP3 is one S and three P. So SP has the greatest S character. So percent S is going to weaken basicity. So we hold on to electrons stronger, so it's not going to be wanting to donate as much. So for example, looking at hydrocyanic acid is a weaker base, pKb of 24, than what, like methylamine H, which is sp2, which is weaker still than methanamine, which is actually pretty basic at 3.36. So the more double bonds to the nitrogen, the weaker the basicity, because essentially we're holding on to that electron pair a little bit stronger. So with that in mind, let's see this off. So non-aromatic involved with hybridization, sp2 and sp1, are less basic than aliphatic nitrogens of the same situation. So if I look at Sorry. Okay. So even though this guy is not using this lone pair in this aromatic ring, that is less basic than this guy. But the essentially the pyridine is less basic than the pyridine, because even though these lone pairs may not be used, that guy's sp2, that guy's sp3. Okay, so looking at amine salts. So pronation of amine will get ammonium salt. That almost anytime you have an amine and you mix in some acid, you're going to see some pronation. But of course, you could always go back the same. So if I have this and I have a HCl, I'm going to form NH4. But the second I add some base, it's going to go back. So don't think too much. While this guy is organic, and especially if it's an amine, organic and poorly soluble, water soluble. This guy is ionic and highly water soluble. So you can actually use those properties to move amines back and forth between organic and aqueous phases when it comes to purifying a compound. You can say put them entirely in the water phase, remove the organic phase, then introduce a new clean organic phase and extract them back into the organic phase and remove the water phase. That way you could separate an amine from its byproducts. So that's an easy way to separate the two. Let's see. So essentially the process would be something like this. You would say, oh, you have organic mixture. So then we mix the organic mixture and we get it to the aqueous phase, subtract the organic, then we get it back to the organic, subtract the aqueous, and now this is pure. And then we can, of course, then evaporate our solvent or something like that, and so we have just a pure compound. Now, things to note about IR and NMR and all that jazz. IR, primary and secondary will have that broad NH stretch. You're not going to see that NH stretch in tertiary because, well, you don't have you don't have NH. It's just NR. So 3200 to 3500. Primary amines will often have two humps. Now, as I said, now you could look for a carbon-nitrogen stretch in the 1000 to 1200 region, but it's kind of hard to see because there's usually a hot mess of other things in the fingerprint region. So we don't really bother to look for that. Now, in proton NMR, NH is solvent dependent, so it's really hard to guarantee where it's at, but it's usually between 1 and 4 ppm. But much like the OH, it's usually a broad singlet. And if you mix in D2O, you can get it to disappear. Now, there's going to be, now this guy is going to de-shield our other, our adjacent hydrogens, but it's going to be shielded a little bit weaker than oxygen because it's less polar, less electronegative. But you'll see some de-shielding. And the carbon-13, you'll see a de-shielding of the alpha carbon between 30 and 50 ppm, adding on to whatever it would already be. So you'll see a little bit of shifting, but it's kind of hard to tell. Now, if you were using a mass spec, which we didn't really learn about this, wish we had some time to learn about this. If we had some time to learn about this, mass spec is guaranteed to tell you whether you have a nitrogen in there. Because of the odd nature of a nitrogen, that it has an even mass, but it can make an odd number of bonds, you're always going to result in an odd mass peak. So you always know whether you have an odd number of nitrogens or not. And that you look at the mass peak and is it an odd number or not. So 1, 3, 5 nitrogens will always have an odd mass peak. So it's really easy to tell whether you have an amine or not by mass spec. But we didn't have time to learn of that, so. Okay, so let's start with reactions with these guys. Talk about reactions with these guys and how to make them, and it'll take us a good deal because we didn't really spend nearly as much time. So we'll start with some review, jumping directly from what we had last chapter. Aldehydes and ketones will react with amines. All types of amines. So we can react with Y and H2. Now, this Y could be an R group. It could be Y could be an H or an R to form an imine. If Y is an OH, it forms an oxime. If Y is NH, it could form a hybrazone. But the basic idea here is in the presence of acid, first we form this OH and HY. And there's one other compound you could form, the semicarbazole, but not as big. And we just essentially form a double bond and whatever the Y group is coming off in water. We're essentially exchanging the oxygen for the nitrogen, and the nitrogen keeps whatever functional group is the most important functional group that's on there. It's going to remove the H's and leave either R, OH, NH, doesn't really matter. It's going to leave those guys behind and form a weird compound. We talked about electrophilic aromatic substitutions of these guys. Let's say of aroamines. So remember that amine is an orthopara director. It's the same thing as oxygen was, due to the aminium resonance. So if I have an NH2, if I, for example, mixed in bromine with iron tribromide, Oh, yeah. I would form essentially, oh, hey, amine would form ortho, para. I added enough bromine, I could add that. Now, strong acids will protonate amine to ammonium. If you made ammonium, you'd make a meta-director. So if I made ammonium, then it would form, you would attack with bromine at the meta. Now, if I used an oxidizing acid like nitric acid could oxidize the amine to a nitro group. So, like, let's see, pyridine. Like, if I tried to electrophilically add to pyridine, pyridine is a meta-director. It's strongly deactivated. You need very harsh conditions to add to pyridine. That nitrogen is actually going to act as a meta-director. So pyridine can often be attacked by an electrophile to form pyridinium, which is even less reactive. So if I put in, like, say, electrophile like Br+, going to be even less reactive. So now, once again, we didn't really discuss this too much. But this pyridine, because it's a meta-director, instead of going through electrophilic aromatic substitution, it could instead go through nucleophilic aromatic substitution, where meta-directors and electron withdrawing groups are actually to the benefit. Now, this is activated through nucleophilic attack and will actually be ortho and para directors. So if I add, trying to remember, nucleophilic substitution. I'm just looking at, aromatic. So if I wanted to add on addition, so if I wanted to add on, for example, base. I'm just trying to look. Let's see. If I wanted to add in hydroxide, I could add on, you might be able to, I'm not sure which would be better, ortho or para, or if you would even add all three. You could probably at least add one. The base would keep abstracting and have a O minus. So we need a weak acid to protonate those again. Okay, so we can do some nucleophilic attack on amines. Okay. Alkylation of amines. So we can do some SN2 on these guys by Rx. So the SN2 mechanisms will only work for primary and secondary because, once again, steric hindrance. You can do this, it forms, you can form ammonium salt, but deprotonation can lead to multiple alkylations up to 3 additions. So you can commonly make a mixture of products, so we got to be careful. So our alkylations, H2 plus, we'll just call this methyl bromide. But it's just a generic RX. So the byproduct is, so well, we're going to attack here. So we're going to have R and H methyl and bromide minus. But now another amine, this is ammonium, that's going to be a quaternary. Another amine can then attack the proton, deprotonate the proton, and generate another alkyl group. So we have R, N, H, and methyl, and we got a lone pair back. So as long as we have more bromine, it could add again. Methyl bromide could add again, and we could then have another deprotonation. So essentially your product is now R methyl methyl. And if you could eventually go to a quaternary amine. You could keep going. So you're going to get, and so this is really complicated kinetically. Depending on how much of your alkyl bromide you have and how much of your amine you have, you're going to get some degree of unreacted primary amine, some amount of secondary amine, some amount of tertiary amine right here, and you can even push it all the way to some amount of quaternary amine. So it can keep adding so long as there is more reactant. So how can we, and that's why does that matter? Well, that means you're going to have a lot of separation to do. You have to separate all your little byproducts from the one you actually want. And so this results in a very complicated mixture that's a pain in the ass to deal with. So there's several different ways to handle this. You can do exhaustive alkylation, which means a large excess of our alkyl halide. If I say one equivalent of my amine with at least 3 equivalents of my alkyl halide, that means in the presence of a base or like carbonic acid, like sodium bicarbonate or sodium hydroxide, we'll get our you'll just completely add all the functional groups onto there. And so you'll get all of the quaternary product. So that's one way we can handle that. The other way is to react with an excess of ammonia so that you only get a primary product. So like I use 10 equivalents of ammonia and 1 equivalent of our alkyl bromide, and you're only going to get our NH3. So that is the other option. Now that kind of limits what we can do, so we can't really do it too many times. But there's other ways we can try to get at that. There's other ways we can get at that. Let's see. So the standard method is going to stop us from getting those secondary and tertiary products. So another way is acylation of amines to form amides. So we can form primary and secondary amines. The same way as like we might acylate aromatic group. So the idea that acyl chlorides are far more reactive than ketones or aldehydes. So we kind of talked about this in the aldehyde chapter. That okay, if you can make an acyl chloride, you can react them with just about anything. So I can take a primary amine, react it with some sort of acyl chloride, carbonyl chloride, and that chloride is an extremely good leaving group. So in a pyridine solvent is a slightly basic solvent, pyridine solvent / reactant, we will form an acyl chloride, an amide, NH double bond O, and a protonated pyridine. That's the reason specifically to use pyridine, because it acts as a base as well as a solvent. Now, how is this actually going? How is this actually? Now, I'll show you the mechanism in just a second, but why is this important? Because you can form this is only going to add one time. We're not going to have to worry about multiple additions. It's not going to react multiple times, so you can limit what you have. Limit what you have. So with that in mind, what's the mechanism? So the acyl group, you have this electropositive carbon around here. That is our electrophile. That's going to be the Lewis acid of the scenario. Action going to be the nucleophile, kicking the electrons up into there. So we have R prime, carbon, O minus, chloride, and H. We're going to have this lone pair. Swing down here, kick off the chloride. That's the first thing that's going to happen. To form our protonated amide. And at this point, our solvent comes in, our basic solvent comes in, and will deprotonate that and generate our product. So it's basically nucleophilic attack on the carbonyl, swings down and kicks off the chlorine, and then we just have to deprotonate this, just like we did. So it's one thing we can go about doing. Let's see. Now, an aryl amide is still an orthopair director, but it's not nearly as oxidizable as, say, a standard amine. So So like, for example, if I have the difference between this is an ortho pair director, but so is this. They're both ortho pair directors, but this one will not give you the same reaction if you put nitric acid in here. Nitric acid is one of those oxidizing acids. It's going to oxidize that nitro group. Well, this, if I put nitric acid with sulfuric, I can add a nitro group, just dandy. NO2. And then, due to the nature of amides, in the presence of acid, I can kick off the amide in the presence of acid, kick off the amide and put it back to amine. Keep our NO2. So nitric acid with sulfuric is going to just oxidize this. And if it still adds, then maybe it's going to add the NH2 meta to it. I think the last one we'll hit is the formation of sulfonamide. Which is something similar to what we've done before, where we add sulfonyl chloride as a group. Works kind of similar. We did tosyl sulfonyl chloride. We'll take our sulfonyl chloride and we're going to have NH2R and add on to this. What's happening? Sulfonyl is willing to accept that lone pair. We're going to kick off the nitrogen. Kick off the chlorine. We have R, S, O, O, NH, 2, R prime. And of course, is pronated. It's positive, so we need a base. I'm going to depronate that. So we're going to have sulfonyl amide. Now, this is very similar to an acyl chloride. A very similar situation. So, just a different type of group we can make. We can transfer that and set for later. So that's probably where I'm going to leave it. I don't want to start in on the Hoffman elimination today. So, but in the near future, we're going to be doing like some named elimination reactions, some other reactions with nitrogen. So we got a bunch of different ones. But, well, that's where I think we'll go ahead and end this for today. So. Okay, so with that in mind, don't forget to turn in your quizzes and speak to you again real soon.